The title of my talk is How Do We Ensure That Trustworthy AI Remains Trustworthy? The stuff I'll be talking about isn't just mine. It's done in collaboration with a number of people. So up there you see some of my postdocs, PhD students, and collaborators who have played a role in the things I'll be showing you in the talk. Trustworthy AI can mean all kinds of things. Within my talk, I will primarily talk about algorithmic fairness and also a little bit about explainable AI. When I wrote the abstract, I thought I would have time for more, but when I was making the talk, I changed my mind. So that will be the topic for now. These are both, by now, fairly established topics. You can find textbooks about them, as you can see on the slide. There are methods out there that you can pick and choose. So if you want to do trustworthy AI, you can. And you probably also will. So with the AI Act being implemented, we will start seeing trustworthy AI algorithms coming into widespread use because people will have to. If you apply for an EU grant now, you have to write an ethics self-assessment. And if you read the guidelines for how to make those, there's a whole chapter about what you should do if you're going to do anything with AI. You even have to specify which pages of your proposal say something about AI, which means you just say the whole thing. And then you have to write something about how you're going to ensure that all your AI algorithms are trustworthy. They have to be transparent. They have to be fair. Or at least you have to do what you can to make sure that they are. So that means we will be seeing a lot more use of these types of methods. But is that good? Well, it probably is good, but is it easy to do it in a way that's good? Is it just a question of using a method and then you are doing things in a trustworthy way? I'll try to answer that question by going through a couple of short stories, if you like. And the first story is a story of label bias. What you see up there is one of the most influential papers in algorithmic fairness. It's a study that was carried out in the US where researchers studied an algorithm that was used to make predictions about people's healthcare needs. They trained an algorithm to predict people's healthcare needs, and they did so without actually knowing what people's healthcare needs were, because how do you know that? So since they didn't know this, they used a proxy, and the proxy that they used was people's healthcare use or their healthcare costs. This was in the US. So people's usage of healthcare services and the costs that are spent on them also depends on their access to healthcare, which depends on their insurance. There are huge demographic biases in who has access to healthcare. And what ensued was that the algorithm systematically estimated that Black people had a smaller healthcare need than white people. Which isn't surprising if you think about it, but if you're just building an algorithm, you might not think about it. And this is a case of label bias. The labels that you're using to develop and train and test your algorithm have a bias in them. And in this case, that bias meant that you were underestimating the needs of Black people. Label bias is actually really common, at least in healthcare. I primarily work in medical imaging, and we often don't know the actual diagnosis of people. We know the recorded diagnosis of people. But first of all, you're only going to get a diagnosis if you actually see a doctor. And even in Denmark, where I live, or in Norway, there are biases as to who's willing to go to a doctor when they're not feeling great. For some diseases, there are more biases than others. And an example that you see on the screen has to do with mental health care, where we know there are biases where males are less prone to go seek treatment and diagnosis than women. In other diseases, it's probably the other way around, either that women are systematically underdiagnosed, or maybe that they even don't see a doctor because they don't realize that whatever they're suffering for is there. Other examples where you run into label bias is any sort of situation where your outcome depends on an action that you take. So one such example would be in the judicial system. If you're trying to estimate whether or not somebody is criminal or whether you think they will re-offend, this is very much biased by whether or not you spend time in prison or not. So this is inspired by another one of the early and really influential cases in algorithmic fairness, where, again, researchers found, or actually investigative journalists found, that an algorithm that was being used to decide whether or not people who were arrested should be let out on bail or sent to jail, they found that this had big biases in the sense that black people, when the algorithm made errors, they put them in jail even though they were not very criminal, whereas white people were sent home on bail and then they reoffended. But these labels that you have, do they reoffend or not, are also biased in the sense that if you actually go to jail, you're actually more likely to become criminal even if you weren't already. So those who have actually been to jail and are let out, and then you check whether they reoffend or not, have a higher chance of reoffending than if they'd never been to jail in the first place. And a similar example would be hiring. If you use AI to try to assess whether or not you should hire someone, again, your data depends on who you hired before. Which means you have no data saying, should I hire this person? You can only check, would I have hired them in the past? So if your hiring is generally biased, then your labels are biased as well. You could also consider label noise, which is a bit different. It's not, then you don't have a systematic bias, you're just making maybe more errors for one group than another. And in healthcare, that could cover a situation where the diagnostic criteria fit better to one group than another. And that happens too. We know diseases manifest differently in different people. But I will mostly be talking about label bias in this talk. So let's just imagine a very simple case. You are building a decision support model to support salary placement for your employees, and you want to make sure that it's fair. And then you imagine that the actual labels that you have in order to test this algorithm has actually been overly optimistic when it comes to the salaries of men. So if you assume that there actually is an underlying ground truth of which income group they should be in, which is what you see in green, looks distributed the same way for men and women in this very synthetic example. And then you assume that in your recorded labels, you are putting a few extra men into the high income category. So extremely synthetic, but nevertheless, let's go with it. And let's say that since you want to check, is my algorithm fair? You have to check you have to decide what does it even mean to be fair. So if you go to the algorithmic fairness literature, you can take one of the books I showed you. You can look up all kinds of different definitions, and they don't necessarily agree with each other. So you have to pick one. Now, let's say that in this case, you have deemed that the equalized odds criterion is good for your case. What equalized odds means is that you equalize all your error rates for your algorithm, so that you have the same true positive rates and the same false positive rates, and thereby also same false negative, true negative rates. One way to think about this is that your resulting algorithm, if you make a ROC curve for each of your groups, in this case the women and the men, then the algorithm, the threshold that you will use for your predictions will put you at the same spot in that diagram. So you have the same false positive rate as the x-axis, the same true positive rate as the y-axis. So the same location in the ROC curve diagram. That's what equalized odds means. You would make this if you think it's equally bad to make false positives and false negatives, basically. So let's say you make this assumption, and then you take a look at your data. And I'm nearsighted, so I can't see what it says up there. But if you look at the top here, you look at the model that you've trained, that you want to test, and you look at it with respect to your recorded labels that have a bias in them. So these, if we look back, would be the orange labels in the bottom, where you are overly optimistic on the salary levels of men. If you look at those, and then maybe you look at differences in AUC between women and men, that's nicely related to ROC curves, and maybe also then look at the true and false positive rates that actually go into the criterion. So you'll see if you only care about AUC, it doesn't look too bad. True positive rate is a bit different, but not too bad. But in the false positive rate, it actually looks quite different. So this means this is actually capturing some of the unfairness that we even put into this data set. All right. So, but if we then look at what this looks like with respect to the true labels, you'll see similar tendencies on the false positive rate, but on the true positive rate, you see the tendency has actually swapped. So, the analysis that you made with respect to your simulated or to your bias labels, the conclusion might be the same. It's unfair, but they're different. So it's inaccurate now that you're using these biased labels. So that's the first observation. Now, if you then follow, and remember, in real life, you wouldn't have access to this thing down here. So you'd be looking at this thing. And assume then that we follow the standard algorithmic fairness pipeline. You apply some processing to this, meaning you can, if these are your two ROC curves, you pick essentially the point along these curves that gives you the best performance, and then you create new versions of your algorithms that fit these. You can do that using randomization. Now, if you do this, then you get what we call a mitigated version of the algorithm, one that's now supposed to be fair with respect to this particular criterion. And then we look at our algorithm again. So this is now the mitigated model, the updated one, and I look at it with respect to my biased labels. And indeed, you see now, everything looks very equal and nice. Great. But these weren't the true labels. The true labels look like this. And here you see, it's actually not fair. So the algorithm is still unfair. And there's no way for me to know because I don't have those labels. I have the labels up here. So it looks like the model became fair, but it didn't. Now, this example isn't that bad because if I compare the situation I had originally, which looked like this, and the mitigated one, which looks like this, now these are both with respect to the true labels, it did actually get better. But it doesn't always get better. Imagine that you'd started out with a model that was completely fair, completely perfect in all respects. And then, because your labels are biased, you measure it as being unfair, and you change it. Well, if it was fair and you change it, it's going to have to become less fair than it originally was. So doing this could actually also have made it even worse. And again, there's no way for you to know. So what do we learn? Well, label bias is actually quite frequent. It's hard to discover unless you actually think about your problem and realize you might have it. And it's hard to quantify. So even if I know that depression is underdiagnosed among men, how underdiagnosed is it? How on earth would I find out? There's no test that will tell you whether someone is actually depressed. So very commonly, the true labels can't actually be observed. So in this case, we are unable to measure fairness. Because we can't measure it, we can't really properly mitigate it either. And we are at risk at creating new biases if we try. That's a great story, isn't it? Let's have another one. The second story is about invariance and demographic invariance of models. One of the big stories of 2022, which is already more than a year ago, was this study. At least it was a big story in medical imaging, which showed that you can actually predict patients' race from their chest X-rays. Now, it's not really new in medical imaging that images encode information. I mean, it's obvious that a chest X-ray encodes gender information, but race? I don't think anyone expected that. But it turns out you can. So this study got a lot of attention, and I have to admit, the first time I saw it, I was like, well, so what if you can predict race? Is that a problem? Does it lead to bias? And one of my good colleagues in the UK actually tested this. And here you can see what the ROC curves of a diagnostic classifier looks like for various classes when you have different races. And again, you can see the curves look very similar, but the thresholds that you would use put you at slightly different locations. So for instance, if you think in terms of this equalized odds criterion, you can see if you just choose your regular 0.5 threshold, you might get slightly different fairness performance, but it wouldn't be that hard to fix it. You can say that's lucky in this case. Maybe there are other cases where it's not that easy. And then a seemingly obvious solution would be to try to remove this race information from your model. Just remove it from your latent features. You can do that. It's just, you just have to actually get your adversarial training to work and you're there. But hang on. It's not that easy. If you do that, what you're doing actually corresponds to marginal invariance, or where you're forcing your latent features to be distributed the same way for all your groups, which is or indicates another statistical fairness criterion that we call independence. What independence says is your predictions have to be distributed the same way for all groups, meaning if you just have binary predictions, your acceptance rate or your positive rates or whatever you call them have to be the same. This will lead to loss of performance if there are any sort of prevalence differences between your groups. Imagine you're studying breast cancer. If you insist diagnosing people at the same rates in groups of women and groups of men, you're of course going to make a whole lot of mistakes. So there are lots and lots of diseases where you have different prevalences among women and men, different races, different age groups, etc. So removing your sensitive feature from your latent features is probably not a great idea. Then you could say, well, maybe I don't need to remove it completely. Maybe I just need to remove it conditioning on classes. And that actually brings me, So let's look at what that would look like. So imagine now that you have two groups of people on the left and the people on the right, and then you have a lot of healthy people on the top group and a lot of people with disease in the bottom group. So you have here prevalence differences. Let's look at what those two criteria would give you. So in the first one, where you insist that these should be distributed, that your latent features should be distributed the same way for both of your groups, you can see very clearly you're going to have a loss of performance. Whereas if you only make this requirement class conditionally, your performance is fine. And this might look good. Let's see what it means for your risk predictions. So, like I said, the invariance criterion means you have to have the exact same distributions of predictions for both groups, and that is what you see here. Whereas if you only enforce invariance conditioned on your actual classes, you are allowed to make differences. That's okay. So you see in the former case, you force the model to make mistakes. They're the ones you see here or here. Whereas in the class conditional case, it looks fine. So maybe that's the solution? Well, maybe, but it turns out that class conditional independence indicates equalized odds, and it indicates a bit more. You can have equalized odds without having class conditional independence. So it's a pretty harsh criterion to ask for. Remember, equalized odds meant you needed to equalize your true positive rate and your false positive rate. And that's already quite a lot to ask for, and now you're asking for more. So it means you will incur a loss of performance if you do this. It also implies that you cannot have group-wise calibration, because you cannot have these two criteria at the same time. We know that. So it might be a solution, but it's not clear that it will be a good solution for you. And let's just again try to understand just how big an assumption it is to be independent of a sensitive feature. So what you see up there is just a simulated experiment where you assume that you don't just have one disease, you have many diseases. That's very common. And that all of these different diseases have tiny little prevalence differences depending on your sensitive feature. Let's say there's a little difference in the prevalence among women and men for each of these diseases. Now, what the plot shows you is that just from your disease labels, you can already predict your sensitive feature. You can already predict, is this a woman or a man? You don't even have to look at the image. You just have to look at whether or not they have the disease. So the more comorbidities you include, the better your prediction of that sensitive feature becomes. This is just another version of something called no fairness without an awareness, namely that you will encode these features if you have a whole bunch of variables that all have a little bit of information about your group dependencies. So what this means, if you turn it the other way around, is that if you want to remove all information, say about gender, you have to equalize in your model the prevalences, the predicted prevalences of diseases for all of these different comorbidities, which means for every one of these, you're making a bit of mistake. So that's a lot to ask for, and you will lose information if you do it. So in conclusion, marginal invariance leads to this independence fairness criterion. And if you just want to check a box, you could already there say, I checked it, great. But, well, it probably isn't what you want in a lot of scenarios. Your class conditional invariance leads to a super strict version of equalized odds, which is very harsh. And what happens if you enforce this is that all those properties that relate even vaguely to your group membership, to your gender, your race, or whatever it is you're interested in, they're going to be aligned. And that will harm your predictive power. Isn't that a great story? So my third story is a tale about shortcuts. And I will bring them together later. They do belong together. Shortcut learning, at least in medical imaging, again, is something that we've been hearing a lot about in recent years. On the screen, I have a few examples. So what shortcut learning means is there's something in your image that correlates with the thing you're trying to predict at training time in a way that you don't necessarily observe at test time. In the first image that you see is an example of calipers. These are annotations made in fetal ultrasound. I work in a project where we work with clinical data coming out of the clinic. And when the sonographers scan in the clinic, well, they're scanning because they want to measure something. So they measure it, and they save the image with the measurement, because then they can go back and redo their analysis later. But that means the images we get, they have these measurements on them. And the way that they make these measurements depends on what they're looking at. So if you're taking a picture of a head, maybe you measure its circumference. If you're measuring something in the abdomen, you'll make this sort of a cross measurement. If you're measuring a femur bone, you'll be measuring the length of the femur bone. And as you do this, the machine will save little letters saying FL for femur length and so on. So there will be lots of information just embedded into your image that carries information about what you're looking at. So let's say that you're trying to build an algorithm to recognize, is it a head, is it an abdomen, is it a femur? It's really easy for the algorithm to just look at those markings, and they do. Another example comes from X-ray images, where it turns out support devices very likely play the role of a shortcut. So imagine that you come into the clinic with some sort of a lung problem. They're not going to take the image first and then treat you. They're going to do it the other way around. They are going to intubate you if you need it. If you have a heart problem, they will give you a pacemaker if you need it, and so on. So that means if you are studying chest X-ray images, a lot of the time they will have equipment in them, or medical devices that were placed before taking the image because the patient needed it. And of course, these correlate with the disease label. And if diagnosing that disease is hard, maybe it's easier for the algorithm to just look at those support mechanisms. Is there a pacemaker? Is there a chest drain? That means you likely have at least some disease, and maybe it also gives you some idea what disease. A third example comes from diagnosing skin lesions, as cancerous or not. These photos are taken in the clinic, and I believe when you come and want to have your lesions checked, what the clinicians do is they circle the ones that they're worried about, then they start taking pictures. If they are worried about something, they put a ruler next to it, because the size of a lesion makes a difference as to whether or not it's likely to be malignant. So they put rulers in order to have information about scale. And for some reason that I don't understand, but I'm also not a dermatologist, they also put these, well, I understand why they do that. They put these stickers that help calibrate the color scale, but they tend to put these near the lesions that they don't think are malignant. And that part, I don't know why. But they do, at least in the data sets that we work with. Those stickers are all on the non-malignant lesions. Anyway, when you build algorithms, what this means is that if the algorithm finds it difficult to look at lesions, it might find it a lot easier to look for rulers and stickers and ink. And they do. So shortcut learning is very much real and very annoying. Now, and then you might say, well, what am I going to do to fix this? And of course, there are all kinds of things you can do. It's really hard to discover, though, that this is really what's going on. And what some of my students have been working on is to try to then remove these shortcuts from the images and looking at how that changes what the algorithm does to it. If you can actually remove the shortcuts without removing anything else, that would be fine. You could train on shortcut-free images. You could use them to test and see what happens and so on. So, the goal is to be able to use this to both quantify and fix shortcut learning. But there is a problem, which is it's virtually impossible to verify whether you changed anything but the thing you think is a shortcut. So if we look back here, in the case of the ultrasound, it's not so hard, because the things that are stuck in the middle, they're small, and you can even take images before and then annotate them, and in that way create images with and without these shortcuts. So there you can actually do it. But if you think about these chest x-rays, what would this person look like if they didn't have a chest drain or a pacemaker? We don't get that data. So everything that we do there is really hard to validate. Doesn't mean we shouldn't try, but it is hard, and that is a problem. And one of the reasons why it's a problem is, while we're pretty sure these devices are a problem, a shortcut for chest x-ray, we also suspect there are all kinds of other features in there that also act as shortcuts. And some of our suspected shortcuts are things like age. You can predict that from images. Gender. You can definitely predict that from images. Now we know we can predict race. Maybe that's an issue. And comorbidities. Maybe some chest diseases or lung diseases are more likely to appear together. And if so, maybe one of them is easier to detect than the other, and you use that as a shortcut. It's really hard to detect. Now, anyway, if we accept there might be shortcut learning, and we accept that we're able to detect race from medical images, and we know that at least in some cases, certain groups are severely underdiagnosed, so there's a label bias, that is a pretty uncomfortable cocktail. Because what might happen is that when you train an algorithm to do diagnosis on a data set where there might be label bias and you don't know about it, but maybe there are some groups that are underdiagnosed in your labels, and maybe let's say that Black people are underdiagnosed. Might happen. And let's say that your algorithm is able to detect, by looking at an X-ray, this is a Black person, and use that as a shortcut to recalibrate the predictions. So normally, if you weren't Black, you'd be this likely to be ill, but because you're Black, and generally you're less sick than other people, you're actually only this likely to be sick. That could happen. That's what we ask the algorithm to do with our loss functions. So models might use demographic variables as shortcuts to recalibrate the algorithm so that it underdiagnoses underserved populations. And if you don't have true labels, you have no way to know. So you're damned if you do and damned if you don't, because, well, everything I told you so far is about things that are hard to do. There is one thing that people are doing that might be promising, which is essentially just to take the last layer of your neural network and try to factor out the effect of the shortcut. You need to know, you need to have a suspected shortcut in order to do that. But if you do, in principle, that should at least reduce its effect. The only issue is you might also reduce your predictive power for your own model. So you have to be lucky for it to work. But it doesn't even stop there. I promised to talk just a tiny bit about explainable AI. Let's say that your model is using image features to encode something about a sensitive variable, let's say race. And your model is using that group membership to recalibrate your predictions group-wise. What a good explainable AI model would do is it would show you all of those features that it used to identify your group membership, because that's part of your prediction. That's important for your prediction. So you might have some sex-specific features and some disease-specific features, and a good XAI model would emphasize the disease-specific features, but it would also emphasize sex-specific features, which might lead you to make all kinds of incorrect not assumptions, but deductions about what's going on. So in conclusion, well, shortcut learning, we're pretty sure it happens. We know it happens sometimes, but it can be really hard to verify and mitigate, especially in cases like just diseases where some of your shortcuts, even though they're physical, it's hard to just measure whether you remove them correctly. And other suspected shortcuts, such as race or gender or age, they are so embedded in the image that it's impossible to know whether you remove those without removing something else. So you do risk removing other information if you try to remove those. And if you have label bias, race or gender shortcuts together, you could get this group-bias recalibration, leading you to underserved populations. And if we don't have any less biased proxies, we would be unable to detect it, and we'd be moving along happily without knowing it. So, where does that leave us? Well, maybe I'm just repeating myself, but the label noise and the bias hurts our ability to measure and mitigate algorithmic bias. We might even introduce new bias if we use them incorrectly. That was the first story. Sensitive groups encoded in images can be used as shortcuts to recalibrate the algorithms. That was the third story. But removing this group information also isn't necessarily an option, because that could force a loss of diagnostic ability, so a loss of performance. And there are some solutions emerging, but the current status is, if you use these trustworthy AI algorithms without thinking, you might actually make your AI less trustworthy. Well, that sounds really hard. Maybe it's even impossible. Should we just not do trustworthy AI at all? No. We should absolutely do trustworthy AI. And to this room, I can say, well, this is amazing. It means there's a whole chest of open problems that we can work on, right? So from the methodological perspective, this is exciting. From the more applied perspective, it mostly means, whenever you talk to anyone who wants to use this, you have to hammer into their heads that they have to understand what they're doing. They have to understand the methods they're doing, and they have to understand what could go wrong if they use them incorrectly. So while the AI Act is great, we need to have incentives also to carry this out well. It's not enough to just pick an algorithm, check the box, and move on. We need to maintain that this is a technical discipline, which again, that's great for us. It's not enough to hire a philosopher, and then you dealt with it. You should totally hire a philosopher. They're great. But you also need to hire a technical person to work with them. Yeah? Or 5. And we need to move away from this really high-pitched trustworthy AI debate where there's a lot of, oh my God, AI is really horrible, let's not do it. And instead go into maybe a more boring debate, or a more curious and problem-oriented debate, where we have technical discussions about what we might do to fix it. So in that sense, I have open positions. Contact me if you're interested. But other than that, I'd actually like to keep it there, and I'd love to discuss with you. Thank you.